So it's my pleasure to introduce our first speaker, Nina Gierasimczuk. So just do a few words to introduce Nina. So Nina obtained her PhD in computer science at the famous Institute for Logic, Language and Computation at the University of Amsterdam in 2010. And that was under the guidance of Johan van Bentum and Dick de Jong. And the thesis was exploring the connections between formal learning theory and dynamic epistemic logic. Since 2016, she has been working in the Department of Applied Mathematics and Computer Science at the Technical University of Denmark, since 2018 as Associate Professor in Logic. Nina's been the recipient of several grants and awards from organizations such as the Netherlands Organization for Scientific Research and the Foundations for Polish Science. Her main research interests lie in the logical aspects of learning in both single and multi-agent contexts and involve computational learning theory, modal logic, and computability theory. So in the last few years, Nina's written several excellent and very accessible papers that really help to build a bridge between belief revision theory and formal learning theory. And I'm delighted to introduce her invited talk today on this topic on the dynamics of true belief, learning by revision and merge. So Nina, the floor is yours.
Now you should be able to hear me. Can you hear me well? Can you hear me? Yes? Okay, great.
Yeah.
Thank you. Thank you very much for the kind introduction, and also I am extremely honored to be invited. I hope I will be able to meet the readability of my papers with this presentation. Let's see how it goes. So the topic of my lecture today is trying to build a bridge, or somehow show you how I see the bridge between belief revision theory and learnability. And by learnability, I understand the notion through the lenses of computational learning theory, or formal learning theory, if you will. So just to warn you, this talk will have very little to do with machine learning per se, but you can say that computational learning theory is actually one of the kind of pillars of machine learning in general. It's a little bit like theoretical computer science in relation to computer science in general. So the plan of the talk is as follows. I will first give you some general introduction, and the introduction will transform into an introduction to learnability. I will explain learnability, the basic concepts on the basis of epistemic spaces, so something that is very familiar to everybody here. Then I will move on to look at constructive kinds of learning, and by that I will actually mean belief revision methods. So the core idea of this talk is that I will simply reinterpret belief revisions, so this kind of very precise engines of mind change, as learnability methods. And then I will look at how well this obtained methods fare with truth tracking. So basically the concept that one of our possible worlds is the actual one, and what we are trying to achieve is a belief in that world. So some sort of access to the knowledge or conjecture that the actual world is the world that the learner would actually pick. And then towards the end of the talk, I will give you some general ideas on how to lift this setup to a multi-agent case by looking into collective learning via merge. And finally, in the end, I will conclude, and also I will tell you a little bit about my recent, and not only mine, but also my co-authors, related work that perhaps could spark some interest in the group here. So, yes. So what we will investigate here today is order-driven belief revision methods in the usual sense. And in particular, we will look at some aspects of their long-term behavior. The long-term behavior that I have in mind here is the question of how good are they as learning methods. And moreover, this question can be made a little bit more precise by asking under what conditions of the epistemic space and learnability can they be seen as reliable learning methods, so that they will actually lead us to true beliefs no matter what. And then I will, in the end, also show you a little bit of how this apparatus of looking at belief revision as learning methods can also lead to some intuitions about the topological characterization of learnability and solvability, understood as this convergence to true beliefs. Also, creation of a model logic of learnability, whose maybe cousin would be a dynamic model logic of belief revision at that of Van Bentham. And finally, I will try to give you basic intuitions about the basic setup for collective learning, where we are looking at many revising agents doing the job in parallel. So learnability in epistemic spaces. What do I have in mind when I talk about learnability? So first of all, the central concept of this talk will be that of epistemic space, and epistemic space is simply a set of possible worlds together with some observations. I here faded away the statement, both at most countable. It's not very important for this talk, but indeed we are interested here in both finite and infinite cases, but countability is this requirement that should be imposed for the results to hold. So it's not only for finite cases. So here we see an example of an epistemic space with 4 possible worlds from S to W. And we have 2 observable properties. And these observable properties can be seen as propositions, of course. So O1 holds over S, T, and U, O2 holds over T, U, and W. You can think of them as evaluations over the set of possible worlds, akin to that setup of a model logic, but you don't have to. So, of course, in certain situations, things that one can observe about the possible world might be different than the stuff that can be expressed in the language that is interpreted over the possible range. But for the purpose of this talk, this distinction is maybe not very relevant. But you can see that quite clearly in certain setups of model logic of observations. But for now, we simply think of possible worlds together with propositions interpreted on them, and we call them observables. So just to make sure, the world S makes the observation O true, but O2 false. And similarly for W, but the opposite. And now S, T, and U make the same propositions true. You're probably used to the representation with a tabular setup when we list possible worlds together with valuations. I think for our purposes, this one is better. So now there will be learners that will learn these epistemic spaces, and they will learn them on the basis of the incoming observations. So this incoming observation will come as a data stream or a stream of observations. I use these terms interchangeably. And a data stream is an infinite sequence of observations from our set of observations. The infinity of it is not actual in the sense that the agent never receives the infinite sequence of course in one go. They only receive the initial finite segment of that sequence. And that initial finite sequence will be very often what we will be using. And here for convenience, I will denote it as the vector over O up to the spot N, which codes the N+1 length of the initial segment of our observations. We count from 0. Now, to make the setup, of course, we are logicians here, so we want to idealize a little bit. So the ideal setup for learning will be the one in which the learner receives sound and complete data streams. So whichever world in the epistemic space is assumed to be the actual world, the learner is assumed to receive everything that is true in that world and only the things that are true in that world. Of course, in finite cases, this assumption is not very demanding. In the infinite cases, it can also be met. In the long run, everything has to be enumerated. These two assumptions I will basically take into account most of the time, and when we relax them a little bit, I will let you know, of course, in advance. So what else is important here? Well, yes, so we have infinite streams, and the learner at any time point is concerned with the initial segment of such a stream. These very idealized conditions of learning under which the streams are sound and complete seem to be maybe too friendly. Maybe you might think that they will actually be too strong, but we can already see under this even generous circumstances that learning methods based on belief revision will fare differently. So they will have, we can already distinguish how good they are under this very friendly circumstance. So now the central concept of the learner. So a learner will be simply a function that has the initial epistemic space. So they know the range of possibilities, and they know how to measure the observation against the possible world. So you can think that the learner is kind of this decidability machine. So they basically are able to decide which observations are true in which possible worlds. That is maybe not very important for people working on belief revision, but from a computational perspective, that would be important. And what the learner inputs, what a learner gets as an input as well is this finite initial segment of observations. So initially it's just one observation, then it grows up to 2, up to n. It keeps on going, and each time the learner is asked to output a conjecture. And a conjecture is simply a subset of this space, so it can be any proposition. And the idea is that the learner, by doing so, simply conjectures, I bet that the actual world is within this proposition, within the subset of S by space. And we will call that proposition a conjecture of the learner. So you can probably already imagine that there will be a connection between what the conjectures of the learner are and what the beliefs of the underlying HGM-like learner will be. But this will be made precise in a second. Before we do that, I would like to also just make some distinctions so that maybe I shape your intuitions about the problems with learnability. So just to skip ahead, learnability will be conceived as the ability of the learner to identify the real world among these possible worlds. One is designated to be the actual world, and the learner, by receiving observations consistent or true in that world, all and only, is tasked to identify the world in question. Now, there might be, of course, very unfriendly circumstance for that task. So for instance, in the case A, you can see an epistemic space in which there are two worlds that are completely undistinguishable, or we would say not separable by observations. So T and U cannot be told apart. I mean, they make the same observations true, O1 arrow 2 and O1 arrow 2. Such spaces are definitely out of scope for us. There is no way to do that. There are also very friendly situations in which so-called finite learnability is possible. And they are also called strongly separated spaces in topology. And here I make a connection to my work joined with Alexandru Baltak and Sonia Smets on topological characterizations of learnability. And in such strongly separated spaces, we always have observations that allow us to somehow uniquely identify which world we are talking about. And of course, here, after receiving such an observation or a combination of observations that allow us to do that, we are done. I mean, the learner can simply say, okay, I know I'm in this particular world. And this leads to the so-called S5 kind of knowledge, so knowledge with certainty about which state we are in. The most interesting case for us is the so-called weakly separated space, and it corresponds to the T0 kind of spaces in topology. And that's the one in which states can be separated one way, but perhaps not the other way. So here we see two states, T and S. T makes O1 true, but it doesn't make O2 true. And S makes O1 or O2 true. So what you can see is that they are separable one way, but not the other. So what would be probably beneficial for the learner is to have some sort of an order on top of their epistemic space so that they are able to hypothesize after receiving O1 for as long as they only see O1. But as soon as they see O2, they will be able to switch to S. But if they don't, then that means that they can safely remain within T as their conjecture. The difference with the previously discussed strongly separated space is that they will never be able, if the T is the actual world, they will never be able to eliminate S as the counter possibility, as the other option, because O1, the only observation that they can see in T, is also true in S. There is nothing that separates T from S. But the order might push the learner towards the most plausible or safe conjecture, and know that such a conjecture will remain valid under truthful information. We can also call it safe belief. And this kind of learning will be what we will be mostly interested in this talk. We will call this kind of learning that is based on an order and safe belief that is held as long as possible. We will call it identifiability in the limit, or learnability in the limit. And for simplicity, I will simply call it learnability. So of course, this case, the learnability with certainty, when we are able to distinguish between two worlds, will be a very strong special case, very friendly conditions for learning. But this one is maybe more interesting because we can still learn, but just in this limiting sense. So just to make this intuition precise, we will call an epistemic space learnable by a learner L if for every state of every possible world in our space, we have as follows. For any sound and complete data stream for the state S, there will be a point N such that from that point on our infinite stream, the learner will output the singleton of the actual world, the state that we generate the information from. So the condition is not that the learner has to stop at that point. They can keep on going. But the idea is that from the learner perspective, it might not be clear that they are already in this phase when they stabilize to the actual world. But from our perspective, when we look from the outside, it is clear that the learner already identified or stabilized on the actual world. And in general, we will say that an epistemic space S is learnable if it's learnable by a learner L. So if there exists a learner. Okay, so the condition is existential here. Whenever we can find a learner that learns a space, we call the space learnable. So now what you can maybe infer from this is that the learnability is not really a very constructive concept. So the idea is that we simply have to prove that such a learner exists to show that a space is learnable, but we don't always have to give the learner that does that. Now, the goal of this talk is to see, okay, perhaps belief revision methods, the very concrete methods of transforming the space, would give us learners that would do this convergence for us. So just before we move on to introducing this belief revision-based learning methods, I would like to first focus on some examples, one of a learnable space and one of a unlearnable space. And here we have a learnable space that is a little bit, well, border line. So it is interesting. There are many uninteresting learnable spaces, but this one is an infinite space, countable. So we have infinitely many states, and we have observations that are aligned in this way. So S makes all the infinitely many observations true. S1 makes everything true except for 0. S2 makes true all these observations except for O1 and O2, and so on. If you think about these states as sets of natural numbers, you can think like, okay, this is just a set of all natural numbers. This one is a cofinite set that complement is 0, but it contains all the rest of natural numbers and so on. These perspectives are dual. Now, what do we mean by learnability? So the idea is that that one of the states is picked as the actual world, and now the learner is supposed to receive the sound and complete data stream of it. So let us take the perspective of the learner now, and let's assume that we are actually given O2. So as a learner, we have the space and we receive O2. Now, as we are tasked with identifying the actual world, perhaps we want to give out a singleton. So say like, okay, this is, I have a best candidate for to be the actual world based on the observation O2. And one idea could be perhaps, okay, I could say, maybe it's S0. And I would now want to say that this is not a good choice. And why is it not a good choice? This hypothesis is overgeneralizing in some sense. So what we are getting here is that this world makes also more narrow observations true, O0 and O1, which were not seen so far. So if S2 in fact is the actual world, we will never kind of be incentivized to change our mind from S0, and we will stay in the wrong forever. So we will be constantly outputting S0. However, if instead our preference order, our underlying plausibility will tell us to point to S2 as the actual world, we are safe. Because if S2 is an actual world, we will never receive any observation that contradicts that hypothesis. So we can keep on outputting that as our learning hypothesis. However, if any of the other worlds satisfying O2 is the world in question, we will, by soundness and completeness of data streams, we will receive observations that hold of these worlds, and then we will be able to change our mind. So for instance, if we receive O1, we will be able to switch to S1 and stay there possibly forever if there is nothing else to see, and otherwise to S0. And this gives us this limiting condition for learning, and by doing so, we actually defined constructively a learner that works on this space. And what is important here in this example is that you probably intuitively, if you're still with me, I know it's early and this example is quite complicated, but you probably have the strong intuition that the learner, the algorithm that was learning this, is driven by an underlying plausibility order on the set of possible worlds. So it actually did put us. It pulled us to S2 in the first place, and then it told us what to do afterwards if the situation or the observations develop further. And this underlying plausibility order will be something that will drive our belief revision methods. Now on to an example of a non-learnable space. It's a very similar example to the one before. We also have infinitely many states, countably many, And then here on top of that, on top of this infinitely many S's, we also have this extra world that is marked by S infinity. And this is a world that has exactly the same valuation, and the one in the previous slide that was called S0. So this one makes all infinitely many observations true. Now this one makes only O0 true, this one makes O1 true, and so on. This one makes 0 and 1 true, and so on. So they are finite initial segments of natural numbers, S0, S1, S2. And then on top of that, we also have all natural numbers. Now, one of the famous, or at least in the old world famous theorems of gold, I think it's the second gold theorem, it actually does point to the fact that this space is a not learnable space. And the argument is that it's one of these arguments with a demon that is trying to deceive you as you try to learn. The argument is that whichever world you stabilize on or wish to stabilize on as a learner, the demon can always extend or limit your observability space by changing which world we are actually talking about, so that you will never be able to correctly identify the world. Let's see a little bit as an intuition here. So if, for instance, we receive O1 as an information, incoming information, then according to our previous reasoning from the previous slide, it would be probably good to hypothesize S1, so that if more information comes in, perhaps O2, we will be able to constructively change our mind to worlds that are kind of satisfy more and more observations. So the Occam's razor principle would point us in this direction. However, as you can see, if we keep on in this tail, infinite tail of finite worlds, what will happen is that if in fact the stream comes from this world in the end, the infinite world, we will never be able to cut off that tail. So we will never be able to change our mind from this S's into the infinite case. If we at some point decide to do that, then what might happen is that the stream will at that point stop outputting new observations, and in fact it will be a stream for one of these other worlds. So in both cases we won't be able to identify the real world. If you are interested in the details of this proof and how it goes in computational learning theory, I can also of course provide you with the reference. However, this is just to establish some intuitions that even though the concept of learnability in the limit is very generous, it still has very clear examples, limitations to it. Yes. So now on to belief revision methods. Order-driven learning, we already had in these examples, two examples before, we saw how our learning methods are in fact driven by some underlying plausibility order. These methods can be very concrete. And we will now see how they relate to each other. So overall, learning and belief revision, they kind of go their separate ways. Even when we talk about rationality of belief revision, very often rationality boils down to rationality postulates, so the axiomatic approach. Perhaps we can somehow extend things to epistemic utility, then rationality, like game theoretically speaking, comes into play, perhaps philosophically speaking. In my view, learning, so the ability of the belief revision to actually converge to the actual world on the basis of sound and complete observations should be part of that notion of rationality. So this is how we will try to supplement that picture. So in belief revision, I don't have to explain it here, but just to show you how I think about it, we have a certain belief set. There is some incoming information, we change to another belief set. this arrow is under a lot of scrutiny. We are trying to figure out if this transition is rational in some sense. So if these two sets relate to each other, what kind of consequence operations we are talking about, how it extends to larger sets, perhaps with the P in it. Now, the truth tracking gives you this idea that, okay, there is a belief set or a possible world that codes everything that there is to know about the situation. This forms like this long-term horizon for learning. And what we are trying to do is kind of reach that world under friendly circumstances of sound and complete streams. And the question is whether the belief revision, so whether this particular transition method will actually allow us to get there. So the order-drivenness of these constructive methods, as we know from general research in belief revision theory, is very often related to the concept that beliefs are given by the minimal states in the space in some way that we also definitely encounter in doxastic model logic. Similar ideas are already present in computational learning theory, and they have been since the 90s. And they are known in the form of co-learning or learning by erasing, when we are looking at Gödel numbers of theories as a certain way of ordering hypotheses or Turing machines. And so this order, the numbers that correspond to these theories or whatever you want to call them, they drive the order of learning. So the learner is incentivized to look for the minimal number, the hypothesis with a minimal number that satisfies the incoming information. And finally, in philosophy of science, this is something that you probably encountered quite a lot in Kevin Kelly's work. The concept of the underlying order-drivenness leads to the Occam's razor principle. And there we can see that rationality is very often based on some sort of principle of parsimony, simplicity of hypothesis. And I hope you had this flavor of Occam's razor when we looked at our previous examples, because this is what it actually is, some sort of ordering of hypotheses based on their simplicity with respect to the observations that they accommodate. So in order to talk about this order-driven learning, we will enrich our epistemic spaces with a plausibility or pre-order, so a reflexive transitive relation. For simplicity, you can think of them as total pre-orders. We take the epistemic space and we add a plausibility pre-order. So this basically tells us, does the agent, they have the uncertainty range. Now the question is, how do they prioritize? What is their prior over this epistemic space? Just a small link to what we actually consider to be knowledge and belief in such plausibility spaces. So knowledge in the sense of S5 kind of knowledge, so certain knowledge, can be expressed as without the orders, of course, because we could say that the agent knows that P if the space is a subset of P. So simply if all the states in our space satisfy P. Now a belief is a weaker notion, and here we only expect that the minimal states according to our pre-order in the space satisfy P. Now, as we will see in some of the results here, this minimality is not always possible to reach. So it might be the case that the space is non-well-founded, so that pre-order doesn't have the minimal element. And then there are two options. Either you say that in such situations, the agent does not cherish a belief into certain things. I mean, it's impossible to establish. And from a computational perspective, the function is simply undefined. I'm fine with that. It's a partial belief. But if we want to have the belief defined, we can define it for non-well-founded spaces in a way that extends the previous definition. And we simply, maybe there should be a certain qualifier here because it's a different semantics, but in such cases, the B will be defined to have this property that we have the order, possibly non-well-founded, so there are better and better possibilities. And what we expect is, for the belief to hold, is that there is a point W, and for all the better worlds, P holds. And then we will say that the agent believes that P in non-well-founded spaces. As you can easily observe, then the mean will be the special case where the orders, P orders, are well-founded. Yes. So now a belief revision method, and you have to forgive this very simplified approach here. Belief revision method is simply a function that takes one plausibility space and an observation, and it outputs a new plausibility space. So note the difference with learners. Learners didn't output the new plausibility space. Instead, they output a conjecture, so a subset of the space. Right? Here we want this to be constructive. So we are looking at the starting plausibility space and we are outputting a new one. And here, because of the kinds of belief revision methods that I want to look at, I'm looking both at belief revision methods that will possibly change the set of possible worlds, and possibly, and this is the important bit, will change the plausibility pre-order. What is perhaps worth noting is that the set of observables stays the same. And here you might ask, okay, perhaps there are possible revision methods that actually revise the paradigm so that the learner actually, based on some observations, they suddenly flip the problem into something else. Suddenly the set of observables changes, but this is out of the scope. It's possible, but it's out of the scope of this talk. So here I probably will have a lot of questions and you will probably oppose what I'm saying here, but the iterated belief revision I will simply take to be the iteration of the R operation on the set. So here we have simply a finite sequence of observations and concatenated with another new one. And we take it to be simply, we look at the previous step on the sigma, and then we do the new revision on the new observable. And so here these observations are taken to be very simple propositions that just code the sets of possibilities. So by now we have the concept of a revision method, and we know that we can iterate it. And by doing so, we obtain the results for finite sequences of observations. And now just to tell you the three kinds of belief revision methods that I will discuss here is conditioning. Conditioning simply eliminates all worlds that do not satisfy the incoming observation. Radical method, you can say that Bayesian conditioning is a special case of that. Then I have lexicographic upgrade. And lexicographic upgrade rearranges the pre-order by putting all worlds satisfying the observation to be more plausible than others. And here, because it's early, I actually have a video for you. I hope you can see it. So here we have a plausibility space, P comes in, all P worlds become better than non-P worlds, or Q worlds become better than non-Q worlds, and so on. So the idea is that everything that satisfies an observation becomes better than all the other worlds. And on top of that, within these two ranges, the order stays the same. Right, so this dynamic picture animation is just to show you the sort of build intuitions about how it works in an iterated sense. Now, if we move on to the minimal upgrade, that is the kind of more computationally feasible contender to a lexicographic upgrade. And in this case, we only expect the best case satisfying the incoming information to become better than everything else. Okay, so let's see what I have here. Another visualization. So we have P coming in and only the best world becomes better than anything else. Yeah. So clear difference. This is very much, I mean, this is a popular method, right? We like it. It's feasible, it's elegant, but well, as we will see, there are reasons to hate it as well. Now, how do we link these two things? So now we want the revision methods to become learning methods. So the statement goes as follows. Every belief revision method R, together with a prior plausibility assignment, generates in a canonical way a learning method based on that prior and revision method. And we will call it a belief revision based learning method. And this method is given by defining the learning method on the input of the epistemic space and the finite sequence of observations. It's learning method, so it's supposed to output a conjecture, not a new epistemic space, but a conjecture. So what it does, it puts on the order on the space and asks the revision method, please revise for me. And then what the learner outputs is the set of minimal states of this revision policy. So you can think of it as the learner being simply like an outside of the car, and the revision method being the particular engine that you put inside, and you can switch these engines and see what kind of results you will get. This also should bear some resemblance to a universal Turing machine. Well, we can implement different kinds of machines on it. So I hope this is clear. The idea is that there is simply a belief revising agent underneath, and the learner is a kind of incarnation of this revision method. They don't output the whole space, but instead they just output the conjecture. So a subset of the space that corresponds to the minimal states. And now simply an epistemic space S will be called learnable by a belief revision method R. So it's a little bit of a abbreviation. We don't say learner based on the revision method, but instead I will just shorten it to learnable by a belief revision method. If there exists a prior plausibility assignment that can be put on this space such that the resulting learner learns S. So note that, again, here we have an existential condition. So the learnability with belief revision will depend on the existence of an appropriate preorder on the space on which the revision method can work. And here I remember when I once talked about it, I think at Brown conference, Hans Roth asked me a question, so what is the agency here? So usually we assume that the agency lies in the revision method itself. Here I would say that the agency is a little bit extended. So it also involves the prior plausibility assignment, something that the agent can to some extent choose. And of course, in this case, the Occam's learners or learners that impose a certain efficient way of order underlying the hypothesis, the revision method, will be more successful than others. This is where the existential conditions come from, but you can of course challenge that. Very often in social choice and in other fields, this order is somehow just given as something that the agent maybe has no epistemic control over. Okay, so now the results in the following slides come from my joint paper with Alexandru Baltac and Sonia Smets. The paper was published after a long period of writing in 2018 in Studia Logica, and it's titled Truth Tracking by Belief Revision. So these are the results, and I will try to give you a short outlines of arguments for two of them. So we will call a learning method universal if it can learn every epistemic space that is learnable. So the idea of the universality of a learning method is that it's as good as anything. So basically it means that if a space is learnable, then this particular learning method will learn it. We investigated our three kind of cases, special cases of belief revision, conditional, lexicographic, and minimal, with respect to this ability to be universal. And conditioning and lexicographic in these friendly conditions of sound and complete streams turned out to be universal as learning methods. on the sound and complete streams. However, minimal revision did not do well under these assumptions. And this result has already been somehow hinted at in previous literature. One was the work of Sonia and Alexandru on belief cycles, and the other one was Kevin Kelly's work on, he calls it inductive amnesia, but he works in a slightly different setting in which he considers the topology to be not the possible worlds, but rather the streams itself, which changes the, but the intuition or the arguments are very similar to this. So minimal revision, very well liked way of revising beliefs, turns out to be not very rational when you have, when you put as a goal identification of the real world. So how do we show that? So this can be seen even on the basis of this very simple epistemic space in which we have 3 possible worlds and 2 observations. And the S3 makes both of them true. S1 only O1 and S2 only O2. Now the idea of the proof is that you can basically, in this simple case, you can see that whichever prior possibility you impose on this space, so however you order the possibilities, there will be always a world that will end up not being learnable under these circumstances. So we will either converge to something else, or we will not be able to distinguish between certain options. So just to, I mean, I'm not going to go through all the cases, but just to show you an example. For instance, if S3 is preferred initially to S1 and S2, and S1 is the actual world, then we will never receive any observations that will contradict S3, and the agent will stay in the wrong forever. So they will always point to S3 because it's consistent with observations with O1 that makes S1 true. So this is the only thing that we'll see, but we will never be able to change our mind. You can say, okay, what about if we do it the other way around? Then again, if those 2 options are more preferred than this one, then what will happen is that if this is the actual world, we will receive O1 and O2. And so what will happen is that we will enter this legendary belief cycle in which we will cycle between 2 better beliefs in the prior forever without ever going deep enough to reach the S3. And this is where this inductive amnesia comes in. And this is a very nice name that Kevin Kelly gave to this phenomenon. Is simply that the minimal revision, because it's so minimal, it doesn't have any built-in memory mechanism. You can say that it's history-free or memory-free method. That lexicographic upgrade has this memory in the sense that it lifts the part of the prior and puts it on top of the rest. So it is a form of memory because it keeps on remembering what was the ordering within the space of options that satisfy the incoming information. And the minimal upgrade does not have that possibility. So minimal revision is unfortunately not a universal learning method. The other result that is perhaps interesting, given what we commonly believe in belief revision theory, is that if we assume the spaces to be always well-founded, so that the minimal states are always possible to find, and so the traditionally understood notion of belief can be checked. So the formula can be model checked in this setups. If we assume that, then none of the belief revision methods are universal. And the example of our first learnable space that I showed you a while ago with this ever-growing space to the right shows this example. So you remember when we started analyzing this example, I told you, okay, we receive O2, what do you stick to as a hypothesis? We were trying to, we decided that the good idea is to stick to the hypothesis that is the rightmost, so to towards the open-ended part of the spectrum. And so if you think about it in terms of the prior plausibility, you can see that what actually we demand implicitly is that there are possibilities that are better and better to the right. So the order is in fact not well-founded. So initially, either the learner has this open-ended notion, non-well-founded notion of belief, or then don't have a belief at all. Yes. So just a small, I'm almost finished, but just a small detour. So some of you probably already have this question or an objection, but what about if we observe the complements? So some of the results that we discussed so far, they only seem so difficult because we don't observe negated information. So our observation space is not closed on complements or observations. And indeed, that's why I previously mentioned that we are working on positive streams only, as mentioned in the slides. But we can, of course, extend the vocabulary of our observations. And this is where algebra and topology comes in handy. So we can say how the set of observables is closed, on what operations is it closed. So one idea would be to consider negation closed space. So whenever we have an observation, we can also observe the negation of it so that it does not hold. And as much as on the purely logical level, this would be a trivial extension to a very trivial part of propositional logic, on the level of learnability, this is a huge step because this leads us from positive observation, you might say unsupervised learning, to positive and negative observation, so that we actually are able to receive information together with a tag of whether it is a positive or negative instance. If we do that, then we have this super nice benefit that we can define so-called fair streams, and fair streams will allow us to relax the notion of soundness of the stream. So you remember I said that streams are sound and complete, so that they enumerate all and only true information in the space. The fairness assumption allows the stream to be wrong for a while. So it allows to make finitely many mistakes. And the idea is that it's fair, so all of them are truthfully accounted for later. So the stream is self-correcting. And under this requirements, we can distinguish the superiority of lexicographic revision because of obviously conditioning will not be universal under this circumstance, because conditioning zeroes out hypotheses that are inconsistent with the incoming information. So we will never be able to recover from errors. And so lexicographic revision is the king, but yes, it's also computationally difficult. Okay, so now in the final 2 minutes, I would just like to give you some insight into our current joint work with Zoe Christoph and Thomas Skafta. I think both of them are with us today in the audience. Maybe they will be able to answer some of the questions on this part as well, or maybe not. No, let's not do that, but they're here. So what do I mean by this extension? So the basic setup, and that's just to establish the base situation. The idea is that we have a group of homogeneous revision agents. By homogeneous, I mean that they represent the same revision method. So they are the same revisers. Of course, this assumption can be relaxed, but just to start somewhere. Now, they start with an epistemic space. So they could be a group of researchers working on the same problem, like we are in this community, for instance. So they have the same epistemic space. But they possibly start with different priors on it, so they have different plausibilities. Their individual streams are sound, just to mimic these friendly assumptions for learning, but individually they are not complete. So agents might not be able to see everything individually, but the idea would be that collectively their stream together is complete. So they see everything that there is to see jointly. And now they revise their beliefs based on such individual streams. And then at each level of this setup, we can expect that perhaps there is some aggregation procedure that takes their epistemic spaces or plausibility spaces and merges them. And we'll call it F. And here we will have a basic table or a picture of this. So we have plausibility spaces of n agents. Now, these plausibility profile, as we call it, it evolves over time. So in the first step, we basically take the first element of the first agents of the stream, we revise, then we take this one as the input for the next step, and so on. Sorry for this symbol, but I really couldn't fit everything here. So here we iterate the belief revision space. Now, the most generous assumption would be that at each stage we obtain the merged profile and a collective learning that outputs the minimal elements of it. And so over time, we receive this sequence of conjectures of the collective learning method. Collectively, you can use a kind of diagonal argument that even we could have infinitely many agents, and so the stream has to be complete together. Now, questions that we are trying to answer in our work are as follows. Which pairs of revision on the individual level and merge generate universal collective learning methods? Which setups generate monotonic collective learning methods in the sense of the sequence? So when does it actually behave in a monotonic way? Under what circumstances? This would be quite good to know because of the halting condition for learning. How should the agents be prioritized with respect to their priors? So perhaps some of the priors, for instance, the alchemist agents should be given more priority than others. Also, what notions of collective distributed beliefs are relevant here? So what is it, how does the correct belief have to distribute in the group to be recoverable after such a procedure is concluded? Also, what would be the effects of communication? So what if in the previous picture, the agents do not take only their own revised plausibility space, but they actually take into account some aspects of the merger in their own individual processes? And finally, can erroneous agents be tracked down and deprioritized in the learning process? And here the idea of some sort of memory comes in handy, where we actually are able to recover from an agent arriving at an inconsistent or empty set. So this is a joint work, as I mentioned, with Christoph and Thomas Skafte. We are still at it. If you have some questions about this part, we probably will be able to answer, but the paper is still in progress. So this is everything that I had to say about it. Learnability depends on an observation function, belief revision method, initial plausibility order, and collectively we can also add the merging method on top of everything. And just to point you to related work, the topological characterizations of learnable spaces are in my joint paper with Alexandru and Sonia in TARC 2015. Since then, we were able to establish a dynamic logic for learning theory that doesn't take into account the belief revision methods themselves, but it has the learner operations inside of the dynamic logic. And we have a sound and complete axiomatization of this. If you are interested, to look more at the restrictions of observability, so how much can be observed, what are these observables, I invite you to look at the paper, joint paper with Thomas Bolander and Andres Lieberman from this year. It's already in the archive, but it will appear in a volume soon. And here we look at partial observability. So agents are not able to observe everything that there is to observe, but they have certain limitations, predictable limitations on that. And finally, a work that very closely relates to this final bit of my talk on collective learners. I invite you to look at Christoph's paper, joined with Olivier Roy and Norbert Gratzel, on priority merge and intersection modalities. One of our central concepts for collective learning will be intersection merge. So then this paper actually studies different effects of priorities on that. And we are also working on it in our joint paper. Thank you very much. I really hope that this says thank you in Vietnamese. Google says so. Thank you for your attention, and sorry it took so much time. I hope we have time for a question.